How could mere calculations, questions, statements, and conclusions lead to one of the largest sciences of our time? How did this all begin? The effect literally affects everything, from plants to animals to cycles, food chains, and ecosystems. In the beginning, it was all natural, but something has changed, and all evidence points to our race. Humans. How could we have such an impact? Civilization, technological improvements? Yes. But we need to turn the clock to know how it all began. More than 100 years ago, after the Industrial Revolution shook the globe.
In the 150 years from the beginning of the 18th century, a revolution transformed the way we think, work, and play forever. This was the Industrial Revolution.
About 50 or so after the Industrial Revolution, the name Alexander Graham Bell sparked conversation from continent to continent.
Alexander Graham Bell was a prominent inventor and engineer who is famous for his development of the telephone. In 1974, Bell began experimenting with the phonautograph, which drew the shapes of sound waves based on the vibrations they made. This led to investments from two wealthy patrons who were looking at sending multiple telegraph messages on the same line. This enabled him to develop his acoustic telephone, and he applied for a patent in 1875. He also worked on early theories of magnetic recording, the basic theory behind cassette tapes, floppy disks, and hard disks. He also invented the metal detector and was one of the founding members of the National Geographic Society. He considered his invention of the telephone as a blight on his scientific career and actually refused to have a telephone in his own house.
But what many don't realize is after his research that led to the first telephone, Mr. Bell began to take a fascination in a concept that is argued about for years, at federal levels and in classroom debates. The infamous greenhouse effect. Well, the greenhouse effect doesn't actually cause this literally, but there are two types. There's the natural greenhouse effect, caused by natural changes, and the so-called human-caused or anthropogenic greenhouse effect. If we turn the dial in our time machines enough to reach the 1850s, burning fuel or caffeine powered everyday items such as irons and coffee roasters, water heaters, stoves, as well as olden-day cars. The glory of caffeine soon faded as rock oil was discovered. Kerosene and gasoline were much more cheaper in comparison to caffeine, so everyone was buying them. Alexander Graham Bell was one of the first people to realize and acknowledge the outcome of increasing the use of these fossil fuels. He coined the term greenhouse effect to describe how the Earth regulates the climate for us to live, but also to explain why the Earth would get warmer. Alexander began looking for other renewable sources of energy to be used alternatively for fuel. He thought of wind, electricity, hydroelectricity, solar panels that would use the sun's energy for electricity, but quickly decided that ethanol or alcohol would be the best energy source to comply with the demands of the future ahead. In volume 31 of the National Geographic magazine, he wrote an article and describes ethanol as a clean, beautiful, and efficient fuel. If not intended for consumption by human beings, it can be manufactured very cheaply. He mentioned a couple of advantages, such as when we burn gasoline or coal, harmful emissions are produced as a result of incomplete combustion, as opposed to the burning of alcohol, which is clean and no detrimental emissions are released. The use of ethanol was seen as a potential continuous supply by Bell, since it is produced by a natural means, from the fermentation and distillation of sugar. Ethanol was also seen as an excellent motor fuel because it could allow for high horsepower in vehicles. This was the issue. Cars that required gasoline to run had low compression engines. Nevertheless, vehicles that would use ethanol needed to have high compression engines that would press, or rather compress, the air and fuel mixture more forcefully in the vehicle cylinders. Moreover, another obstacle was the amount of alcohol produced would not suffice the current demands at that time, let alone the demands of the future. All these factors combined denied alcohol the chance to be substituted for gasoline in Bell's lifetime. But today, almost 200 years later, a blend of 15% of gas and 85% ethanol to create E85 is widely used around the globe, popularly as a fuel in power flex fuel vehicles, or FVVs. According to the U.S. Environmental Protection Agency, the use of ethanol in FVVs actually, quote, reduces the country's dependence on foreign gasoline, since it is a renewable energy source, locally produced, as well as resulting in less emissions from these vehicles that would add to more greenhouse gases in the atmosphere.
David here, and behind me is a car you might remember. This was actually the Paxton Coyote 5.0 I reviewed not too long ago. When I reviewed this car, it was around 580 wheel horsepower, but now it has 700 something horsepower, with one difference. How did that happen? How does this car go from 580 wheel horsepower to 700? And that is the magic of a fuel called E85.
In addition, if our famous inventor was still alive today, he would be pleased to know that research on ethanol as a fuel is continuous and certainly progressing. Now down the road, we'll observe another mark in the world's ever-lengthening timeline, 1896, when a man by the name of Svante Arrhenius, made an earth-shattering discovery, or should I say, a greenhouse-shattering discovery. And what he did was he created a model which displayed the influence of carbon dioxide in the air on the temperature on the ground. This was his model of the greenhouse effect. It describes the way the atmosphere retains the heat emanating from the ground, dark rays, in contrast with that emanating from the sun, light rays, which is let through. He referred to dark rays as what is now known as infrared or thermal heat energy, and light rays as ultraviolet radiation from the sun. In 2005, an article from a popular UK newspaper, The Guardian, titled Svante Arrhenius as the father of climate change. His theory and his model were triggered by a particular interest he took in 1895 in an ongoing debate that scientists at that time were obsessed with: the cause of the ice ages. As Ian Sample, author of the article, writes, could it be, he wondered, that vast swings in the levels of atmospheric CO2, lasting tens of millions of years, were the trigger? And indeed, it was. Arrhenius already knew that there was a relationship between carbon dioxide and Earth's temperature. Joseph Fourier, a French scientist, discovered this, quote, who realized that certain atmospheric gases shrouded the planet like a bell jar, transparent to sunlight, but absorbing to infrared rays. With this knowledge, Arrhenius began to figure out exactly how much carbon dioxide and water was in the atmosphere, and kept heat in the Earth's closed system. Along the way, he had a number of run-ins with feedback loops, such as the water vapor feedback loop and the carbon dioxide and global temperature feedback loop. Another couple of years after, as Arrhenius describes as tedious calculations, he finally concluded that if the CO2 levels were halved, there would be a temperature decrease by 4 degrees to 5 degrees Celsius, as opposed to if they were doubled, Earth would undergo a 5 degrees to 6 degrees increase in global temperature. But as he was the first to give out actual numbers, it wasn't dumbfounding that he wasn't entirely accurate. As scientists of our century have said that it's more likely for global temperatures to rise by 2 degrees to 3 degrees Celsius.
If global average temperatures warm more than that, will greatly up the odds of new and worsening climate catastrophes. Stay below that mark, and we may be able to avoid some of the worst aspects of global warming. Think super droughts, mass extinctions, and extreme sea level rise.
And as any theory at that time, the scientific community argued for years and years, on and on, about Arrhenius' conclusion. It was either constantly backed, then argued about, then criticized. But 11 years after his demise, he gathered many supporters when Guy Callendar, an English engineer and meteorologist, was intrigued by the warming of the planet. He stitched the facts together from other scientists, namely Arrhenius as the major one, and resulted with the temperature measurings from the 1900s that showed a conspicuous rise. He checked CO2 levels in the 19th century as well and discovered that these carbon dioxide levels have increased by about 10% in 100 years. After extensively studying Arrhenius' model, Guy concluded that indeed the planet is warming because of CO2 levels and that there is some sort of correlation. And as The Guardian puts it, the existence of an increasing greenhouse effect was hotly debated until the post-war funding of the 1950s kicked in and researchers began to get firm data. In 1956, scientists, namely Gilbert Plass, confirmed the correlation between carbon dioxide levels and temperature. He learned that an increase of carbon dioxide in the temperature would increase the amount of infrared energy radiated back to Earth, and industrialization would certainly speed that process up. Around the 1950s, the scientific community began to warn governments as global warming would, quote, become a serious issue in the future. In response to this, the US government began to task people to find more information about, in quote, what many believed were the direct effects of a warming world. Readings were taken of the thickness of ice sheets, the data that was released in the 1980s, 40 years after, and it was concluded that they uncovered that the ice was melting at an astonishing average rate of 40% thinning by 1.3 meters since 1953. One of the researchers involved in the recording and melting of ice sheets actually figured out something which allowed the greenhouse effect for many supporters. Many scientists at that time believed that when emissions of carbon dioxide we would release, the ocean, being a large carbon or a heat sink, would store all the carbon dioxide. Charles Keeling discovered that the industry's emissions were taking carbon dioxide levels in the atmosphere to skyrocketing levels as oceans were not absorbing carbon dioxide from industries. It was a seminal discovery. For the first time, scientists knew that the oceans weren't going to absorb all this carbon dioxide, says Mike Hulme at the Tyndall Center for Climate Change Research at the University of East Anglia. However, despite a lot of the evidence uncovered, there were still many who didn't believe that the anthropogenic, human-caused greenhouse effect would become such a problem. At that time, in the 1970s, computer models only showed a 2 degrees Celsius increase in hundreds of years. By the 1980s, however, climate science or climate change science had become a mega science stretching over many different fields of study. Physics, chemistry, biology are just a few to name. And as scientists joined the global research team from different fields, they, quote, each attacked the problem from different angles. It was this big collaborative process that many techniques were introduced to find more information. In 1982, one of these techniques blew the others out of proportion in terms of how much information was yielded. Proxy records, namely ice cores, are stores of information that can be measured to give clues to what the climate was like in the past. Other proxy records include tree rings, coral reefs, caves, rocks, and ocean sediments, though ice cores took climate science by storm.
This frozen library, the National Ice Core Lab in Denver, Colorado, has ice from all over, kept at minus 35 degrees. The oldest core here goes back some 400,000 years. Here, really ancient ice from Greenland in the north and Antarctica in the south reveals Earth's climate history. Let's see what cores like this can tell us. First are those layers I mentioned in the New Zealand snow. They've turned to ice and we can count them. Summer, winter, like tree rings, we can date the core. Other cores tell other stories. Look at this. It's the ash of an Icelandic volcano that blew up to Greenland 50,000 years ago. Cores hold other and even more important secrets. Look at these bubbles. They formed as the snow turned to ice and trapped old air that's still in there.
There are air bubbles in the ice in Antarctica and Greenland, and they've been trapped there for thousands of centuries. And when scientists began to drill deep into the ice, they extracted these long ice cylinders, which were then given the name of ice cores. The ice found at the bottom of the cylinder could be up to 800,000 years old. In comparison to the top of the ice core, which is very recent.
Looking at the cores, we see a pattern that repeats. 280 parts per million of CO2, then 180, 280, 180, 280.
By analyzing the chemistry of the oxygen atoms in the ice, you can also see the pattern of rising and falling temperature over time. Colder during the ice ages, warmer during the interglacial periods. Now put the two lines together, and you can see how closely temperature and carbon dioxide track each other. They're not exactly alike. At times, the orbits caused a little temperature change before the feedback effects of CO2 joined in.
But just as we saw in New Zealand, we can't explain the large size of the changes in temperature without the effects of CO2. This is the signature of natural variation. The cycle of the ice age is driven by changes in Earth's orbit, with no human involvement.
But here's where we are today. In just 250 years, since the Industrial Revolution, we've blown past 380 with no sign of slowing down. It's a level not seen in more than 400,000 years, 40 times longer than the oldest human civilization.
So you would have this big cylinder, which is a climate timeline basically, air bubbles, and whatever was in the air at that time is well preserved. Scientists test for various gases at certain times in a layer of the ice core. From this, they know exactly how much water vapor, carbon dioxide, methane, and other greenhouse gases were present in the atmosphere all those years ago. The amount of dust each annual layer indicates the environment at the time the dust was deposited, as well as the isotopic concentration of the water would indicate the temperatures of the environment as well. And this proved to be a worthwhile discovery, as the scientific community now had another medium to compare greenhouse gases to and their levels to that of the past, when the Earth underwent many different stages, like the interglacial periods or warming periods and the Ice Age. As scientists began to graph this data, they noticed that the global temperature range is not as high as it has been in the past, but the greenhouse gas levels are the highest now when compared to the past 800,000 years ago. What worries them today is the alarming rate that the globe is heating at. A group of scientists found something quite astonishing very recently in Alaska.
As we peel back the layers and turn back the clock.
That is unbelievable! Palm tree in Alaska.
As technology began to advance, we could produce better computer models in comparison to the aforementioned ones from the 70s. We were able to find so much more evidence that humans were the cause of current climate change. They would compare a world with and without humans. Without humans, if natural changes were occurring, Earth's temperature would actually decrease according to this graph. But with human effects, the data matches what's going on right now. The scenario fits. The temperature is increasing, and it's pretty evident that humans are the cause. The ice cores, proxy records, and computer models were all becoming evidence too great to ignore. In 1979, the first World Climate Conference was held in Switzerland. In 1988, the UN held the first intergovernmental panel on climate change to, quote, review relevant research. The IPCC is a group of several thousand scientists who summarize the latest scientific research on climate change and have been doing it for more than 25 years. However, the Kyoto Protocol of 1997 really began to emphasize the importance as to how we would mitigate climate change and how important it is for the world to reduce greenhouse gases. It was negotiated that developed countries would reduce their greenhouse gas emissions by 5.2% below 1990 levels by 2012.
Will recommend the adoption of this protocol to the conference by unanimity.
In 2005, however, this was reviewed as the protocol entered legal force. More than 140 countries approved, as carbon dioxide levels alone stood at, quote, 372 parts per billion, higher than at any time in the last 800,000 years. The IPCC, Intergovernmental Panel on Climate Change, still meets every year. And here you can see some of the topics they've discussed. In 2013, they talked about the physical science basis on climate change. And in 2014, last year, they talked about the mitigation of climate change. What's miraculous is that when you tie all of these loose ends and pull them, they end up in the same place, where many people of the past influenced all of this research and knowledge that we have today. They are not here now, but what they began so long ago, so many years ago, sparked the beginnings of a passion, of a science that one could say literally encompasses and dominates the world. It affects everything at large. It's all based on the human race, on us and the future generations, of how we will use this knowledge and make changes, whether it be individually or as a global community. But it all goes back to the efforts of the scientific community now, in the past, and most significantly to those from way back. To simply say that it began in the minds of a few men. The world has changed. It changes every day, but they predicted it. It's well over magnificent, is it not?